Okay, in this lecture, let us talk about preemphasis and deemphasis. If you recall, in the last lecture, we discussed the effect of interferences. That interference is due to single tone interference, like single tone interference signal, like AI times cos of omega c plus omega I times t. Okay, this is what we had in the law, and this one will come and interfere with your desired signal. And then finally we got the output of the frequency discriminator is equal to 1 by 2 pi times kd ai by ac times omega I cos of omega I t. Now if you write this omega I as 2 pi fi, then this is equal to 1 by 2 pi kd ai by ac, then 2 pi fi cos of omega I t. Now this 2 pi will get cancelled. This is equal to k suffix d ai by ac times fi cos of omega I t. So this is for your fm yd of t, and this is for your pm signal phase modulation. Now if you plot the magnitude versus frequency, then it looks like this, fi, and this is your yd of t. Now your phase modulation exhibits a constant magnitude, whether the frequency is very low or little larger. But on the other hand, your frequency modulation has a linear slope like this. So up to this point, let's say up to this point, your frequency modulation is better. Okay, but after this point, let's say a, and beyond a, your frequency modulation is not good. So we discussed somehow we need to bring this portion to come down, maybe like this. Okay, if I introduce a slope like this, let's say this is positive slope, it is increasing at the rate of fi, and you introduce minus fi from this point onwards, you introduce like that. If you add this plus fi and minus fi, then it becomes a constant line like this. Therefore you get this kind of behavior. If you use a filter which is called a deemphasis filter to emphasize larger frequency, therefore whatever happens at beyond this point, this point when f is greater than fi, then it is increasing like this, you bring back to down. So we use a filter, let's say a low pass filter. Basically what do we want to do? We want to make sure that the amplitude increases with the frequency, the filter response will be smaller at that frequency, therefore the amplitude will not increase. So the FM discriminator response is increasing like this. Maybe I'll draw one more time. It is increasing like this. So let's say this point is A and this point is B. Now I will allow the filter response to decrease linearly in opposite direction. So opposite direction like this with the negative slope. Now if you multiply this AB with the AC, then the product of these two becomes a constant. It will be a constant like this, because AB has a positive slope and then AC, the line AC has a negative slope. Such a low pass filter we call it a deemphasis filter. Deemphasis filter. So by using a deemphasis filter at the discriminator output, the effect of higher frequency components can be controlled. That means this growth is arrested. One typically use a simple RC filter of constant amplitude, and this like this. Okay, let's say this frequency is f3 3 dB frequency, and this point is, let's say, f dash, and this f dash is equal to f3. So you design a low pass filter such that the cutoff frequency occurs at this point, that should be equal to your f dash of your response, your discriminator. So the frequency response is like this for your D emphasis. So this is the frequency response. So let me draw the figure one more time so that one second, like this, it is increasing like that. Now you multiply term by term, let's say this value is 1. So what will happen? This portion is multiplied by this portion, is multiplied by, okay, this portion. So no change, right? If you multiply those two guys, no change. But after f3, this point, your cutoff frequency f3, then what happens? Your response is growing like this, but on the other hand, your filter response going down like that. So essentially you are multiplying these two guys. If you multiply those two, then what will happen? Instead of growing, up, it is bending like this. Okay, so when you combine this linear response with okay, so with your filter response, then this becomes almost a flat response like this. So the combination of your linear response with your low pass filter response will give you an overall response like this. It comes like this. Maybe I'll delete this. So the combination of your filter and the linear response becomes an overall response like this. You will get a flat response. So obviously the value of f3 would be less than w, because we are anyway considering frequencies less than w. So choose an appropriate value of f3, 3 dB frequency, where f3 is the cutoff frequency of this low pass filter. Then you can compensate this linear growth. This linear growth can be compensated. Growth is compensated. So therefore, let me write down the points. Choose an appropriate cutoff frequency less than bandwidth of the message signal. Okay, that's it, and there you are. So this is but there is a problem here. Okay, the problem is that if the input signal has a bandwidth larger than this cutoff frequency, this higher frequencies will be attenuated, right? See, you are putting a low pass filter, let's say it has unit magnitude up to f3, no problem, but afterwards it is, you are giving you are giving attenuation. See, in this region no problem, because you are multiplying the signal by 1, so no gain and no attenuation. If you have a signal and that signal is multiplied by 1. That means what? It is nothing but no gain, no attenuation. No attenuation. So this no gain, no attenuation occurs in this frequency range 0 to F3. So 0 Hz to F3 cutoff frequency, no gain, no attenuation. But the moment you go beyond F3, because your message signal bandwidth is beyond F3, let's say this is my W is equal to 15 kilohertz, and let's say this F3 equal to around 9 kilohertz. So whatever the frequency components that you have from 9 kilohertz to 15 kilohertz, those will be attenuated by the low pass filter. Okay, we don't want that to happen. For example, if you are using some music instruments like guitar or violin or something, it produces at very high frequencies. Now, if you give some disproportionate attenuation, then the nature of that violin sound or guitar sound will be lost. Okay, so therefore, we want the output to be a replica of the input, but because of this attenuation, what happens? You will not get the replica of the input. Essentially, your filter is distorting the message signal. Distorting the message signal. So, see, we proposed this de-emphasis for some reason, but this de-emphasis is good, okay, for bringing down this interference. But on the other hand, it is giving unnecessary attenuation. Because of that attenuation, whatever the frequencies you are having greater than F, those components will be distorted. That is an undesirable thing. 0 to F3 no problem, okay, it is not giving any attenuation, no gain. Even if it gives equal attenuation for everybody, no problem, equal gain for everybody, no problem. In fact, that's what your amplifier is doing. Okay, when you design an amplifier, that amplifier is amplifying all the frequencies equivalently. When I say the gain factor is 15, then all the frequency components are amplified by the same amount of 50. So in that case, no problem. Or if all the frequencies are attenuated by the same amount, then also no problem. But here you are doing some kind of partiality. So from 0 to F3 no problem, okay, you are amplifying or you are not doing any amplification, no attenuation. But beyond that you are giving the attenuation, it is coming down. So that is a problem. So the filter is distorting the message signal beyond F3. So what can we do about that? Okay, we are attenuating at the discriminator output. So after discriminator only we are keeping this de-emphasis. So the discriminator output is attenuated at the higher frequency. We are attenuating the higher frequency components which may be present in the input message signal, for example violin or guitar or something like that. So to take care of that, the simple thing that you can do is put a compensation at the transmitter itself. So in the receiver I am giving some attenuation, right? I am giving some attenuation. So what you do is you increase this attenuation, exactly opposite thing you do in the transmitter side. So in the transmitter you have message signal m of t. M of t is given to FM modulator, right? FM modulator. Now instead of giving this m of t directly to the FM modulator, you give m of t first to pre-emphasis, then give it to FM modulator. In the pre-emphasis, what you do is you have a filter like this, and then it increases like this. Therefore, beyond the frequency of 3, you are giving the gain for the frequencies from F3 to W. So whatever you are attenuating in the receiver side by using de-emphasis, the same thing in the reverse direction what you do at the transmitter itself. So increase the gain of the frequency components which are above the F3. Okay, so you are keeping a compensation at the transmitter itself. That means you pre-distort here. It is distorted, pre-distort. In the demodulator you put a like this. If you take this portion and this portion, if you multiply, then it becomes constant. So you are bringing back to the normal amplitude what it was. Therefore, at the transmitter, you pre-distort the message signal to take into account the fact that you are going to do this attenuation at the discriminator output at the receiver. So you have a filter, you carry out your FM modulation, that is called a pre-emphasis filter. Okay, after pre-emphasis filter, you do the frequency modulation, and then at the receiver, after discriminator, you keep the de-emphasis filter, which does the reverse or opposite characteristics of the pre-emphasis filter. So pre-emphasis and de-emphasis, both of them have opposite characteristics. Therefore, the distortion will be removed. So pre-emphasis filter, it is actually a filter, pre-emphasis filter at the transmitter. Okay, at the transmitter before modulation, before giving your message signal to the modulator, you do this. And de-emphasis is a filter at the receiver after the discriminator. That's it. Okay, so if you do that, then if you multiply this portion and this portion, these two guys, let's say this is my pre-emphasis filter HP of F, and this one is HD of F, de-emphasis filter. Let me draw the figure here. It is constant and it is increasing in this point, and the same thing, this also constant, and then it is coming like this. This is de-emphasis filter HD of F, and then pre-emphasis filter HP of F. If you multiply these two guys, then it becomes a constant line. So therefore, my overall response is going to be HP of F and HD of F is equal to 1, because it is constant, right? Look at this. This line is a constant line. Let's say it is equal to 1. Okay, so what we are saying is, let's say my pre-emphasis filter has a transfer function called HP of F, and the de-emphasis filter has a transfer function called HD of F. Then the pre-emphasis filter and the de-emphasis filter must satisfy the condition, this constant of 1. If it is not constant, then we will be in trouble, because some frequency component will be highly attenuated and some frequency component will be not attenuated or amplified. So there is some disproportionate, so that if the things goes in that way, then your complete structure or shape of the signal will be disturbed. So you will get a distorted version of the input signal, message signal. So distortion happens. So that should not happen. Therefore, your HP of F and HD of F must be equal to 1 for mod of F less than W. The pre-emphasis transfer function, pre-emphasis filter transfer function HP of times the de-emphasis filter transfer function HD of F should be equal to 1. So they should not cause any distortion. That's what we are trying to say. Their product should be equal to a constant value. If it is constant, means what? It is giving equal amount of amplification for both for all the signals range. So pre-emphasis filter should be such that over the frequency band of interest, that is from 0 to W, the product should be a constant. In particular, if you take the de-emphasis filter, it goes like this. Up to this portion, no problem. Okay, so let me then let's say this area is A and this point is F3. So in particular so the de-emphasis directly affect in the red shaded region. Okay. But in the green color shaded region, no problem. Okay. So in this region, it is anyway constant, more or less. Therefore, no problem at all. But basically, what we are saying is your FM system now looks something like this. So you take M of t, you put a pre-emphasis filter. It's with the transfer function HP of f. Then you give it to FM modulator, okay. In the receiver side, what you do, you take this, give it to band pass limiter first, band pass limiter, that is hard limiter followed by a band pass filter, right. You put an antenna here, this is my transmitting antenna. In between many blocks are there, I am not putting that. Then FM discriminator or demodulator, and this, then give it to de-emphasis filter. That's it. And then finally you got M of t. So the message signal M of t, instead of being sent to the frequency modulator, directly, it is first pre-distorted by your pre-emphasis filter. So it is pre-distorted to take care of the fact that there is a de-emphasis filter which otherwise will distort the signal. So it is pre-distorted by using a pre-emphasis filter. So this filter has a transfer function of HP of f. The output of this filter is given to your FM modulator. Okay, so the output of this pre-emphasis filter is sent to the FM modulator, and this is what transmitted by your transmitting antenna. Okay, at the receiver, what you do, you just send it to the band pass filter. This is my receiving antenna, and pass it to your band pass filter. And we have discussed the purpose of band pass filter. Band pass filter is nothing but a hard limiter followed by band pass limiter. Band pass limiter is nothing but a hard limiter followed by band pass filter, because it removes any envelope variations. If there is any change in amplitude variations, that will be removed by this band limiters, and you will get a pure sinusoidal waveform, pure FM waveform. And then give it to FM discriminator, and then again whatever period distorted, that will be removed here. So finally you have the de-emphasis filter with the transfer function of, let's say, HD of f. Okay, and that de-emphasis filter will hopefully produce an undistorted message signal. So this is exactly opposite of your pre-emphasis filter. That means the job of the de-emphasis filter was to attenuate with a higher frequency interference that would come out with the large amplitude at the discriminator output. So the job of the pre-emphasis filter is, since the higher frequency components of the signal gets attenuated, so you emphasize. When I say emphasize, what do I mean? Emphasis means here I mean amplify. Okay, so in the pre-emphasis, amplify the higher frequency component. Okay, amplify the higher frequencies at the higher frequencies of the signal or higher frequency component of the signal at the transmitter. De-emphasis means attenuate. De-emphasis means attenuate the higher frequency component of the signal at the receiver. So that's basically what we intend to do. When you do that, there is a slight side effect. Okay, there is a slight side effect in as far as the modulator is concerned, because if you remember, the peak frequency deviation will depend on the amplitude, particularly in the case of FM. Okay, amplitude of the higher frequency components and more. Okay, so the peak frequency deviation may slightly increase as a result of this pre-emphasis, but that is hardly a major problem to worry about. Typically, if you take for example an audio signal or a voice signal, the higher frequency components are slightly lower in strength. So even if you pre-emphasize, that will not affect. Okay, generally if you take our practical signals like music or voice, this higher frequency component generally has low amplitude. So even if you amplify the higher frequency component using our pre-emphasis filter, then there will not be any problem. So one has to therefore guard against the fact that you are further attenuating them at the receiver by using de-emphasis filter. So we must amplify them slightly at the transmitter itself in order to compensate this distortion happened at the output or after your discriminator. So the effect of the de-emphasis filter is taken care of. So once again we will come back to discuss free emphasis and de-emphasis filter and these methods of and there we will discuss like how to improve the performance of FM receivers once again when we discuss the effect of noise later on, because in this lecture and in the past lecture we did not consider noise, we only considered the interference. So that interference can be reduced by using de-emphasis filter after the demodulator, after the discriminator. Okay, the same kind of argument we can extend, the pre-emphasis and de-emphasis in the system where the noise also considered. Okay, so that's all about pre-emphasis and de-emphasis. Now let me move on and let me talk a little bit further about FM receivers. So I think you all familiar with FM broadcasting these days. Okay, FM radio for example, and all the frequency band. The frequency band is, so these are standard value. Frequency band is 88 to 108 megahertz. Typically, if you have multiple FM transmissions taking place in a region, because in our country, in the city of Delhi or Mumbai, we have too many FM broadcasting stations. Okay, so but if you have multiple broadcasting stations in the same neighborhood, we like to ensure that the transmission frequencies of each of the stations are well separated, otherwise there will be some interference. Now how much should the separation be? Let's say I have station 1 and station 2, both station 1 and station 2, how much they should be separated. So let us make an estimate. We mentioned that the peak frequency deviation in typical commercial FM transmission delta F is 75 kilohertz. Okay, it is of the order of 75 kilohertz. Suppose we are transmitting music, its bandwidth is about let's say W is equal to, if it is voice no problem, you can stop at 5 kilohertz, but if it is music you need to consider up to 15 kilohertz. So the approximate bandwidth of the FM would be, what is the bandwidth formula? 2 times delta F plus FM. So 2 times delta F is 75 kilohertz plus FM is 15 kilohertz. So this is equal to 180 kilohertz. So this is the bandwidth of your FM system. For each channel the bandwidth is 180 kilohertz. So that means successive transmission station should be separated from each other by about 200 kilohertz, taking about 20 kilohertz as a guard band. See, this is my frequency band. Let's say this is my 88 to 89.8. This is my first channel, and in between is space for 10 kilohertz as a guard band. Okay, and this side also you put another 10 kilohertz for guard band. Then this is next to 10 kilohertz for the second station 2. Okay, 88 point. So this is, what am I doing? I'm sorry. 88 megahertz. 1 second, hold on. This point is 88 megahertz. Then you add 1.8. Okay, 88.118. Then 88.19, and then 89. So like that you can add it up. Okay, so therefore the successive stations are separated by 200 kilohertz. This one will be 88.18, and this point is 88.19, and this is 88.2, station 2. Then this one will be 88.38 and 10 kilohertz guard band, so 88.39, and this one will be 88.4, like that. So this is my station 1, station 2, and so on and so forth, like that. So each channel has 200 kilohertz bandwidth. So roughly 88 minus 108, so you'll have 20 megahertz bandwidth. So 20 megahertz bandwidth divided by 200 kilohertz. Okay, so 20 10 power 3 divided by 200, right? Then cancels 10 power, so 200 channels you can have in this frequency range. 100 channels. 88 10 to the 6 divided by 108 88, so this is 0, then 20 megahertz. Okay, 20 megahertz is the your frequency band, FM frequency band. Now 20 times 10 to the 6 divided by 200 times 10 power 3, so 1 by 10 times 10 power 3. Okay, so this is equal to 100 channels. So in a city you can have at the most 100 channels, 100 FM stations. Okay, you cannot have more than that. So a typical separation between various transmitters, okay, I mean separation of carrier frequencies will be of the order of 200 kilohertz. And this 200 kilohertz is for your monophonic receivers. And FM is well known for stereophonic transmitter and receivers. Okay, monophonic means single channel receiver. Single channels. Okay, and typically the intermediate frequency IF is 10.7 megahertz. See, the input frequency range will be 88 to 108 megahertz, but you put a super heterodyne receiver and finally you convert into 10.7 megahertz. And this 10.7 megahertz is the standard value. Okay, and this is coming from the concept of intermediate frequency in the super heterodyne receiver. So the concept of super heterodyne receiver is equally valid for FM receivers also. Whatever we do for AM receivers is also carried over to FM receivers. Okay, all the advantages of the super heterodyne receiver would carry over to the FM receivers. Okay, so let me stop at this point. Next time, in the next lecture, let us talk about stereophonic FM broadcasting. Stereophonic FM broadcasting. Okay, so thank you very much.